Hello and welcome to this session on data transformation. A lot of data science beginners often ask me how to improve the accuracies of the model, even beyond model tuning techniques. Answer to this question lies in effective data pre-processing methods. So I'll be talking about data transformation techniques in general and two of the most popular techniques in data transformation: normalization and standardization in more depth. Let's start today's session by defining the agenda for it. We'll start off by understanding the need for data transformation. Then we'll see what does scaling versus transformation mean. A lot more often, people interchangeably use scaling and transformation. We'll then look at several transformation techniques, out of which we'll pick up normalization and standardization for today's session. Now, quite often it happens that one feature or two features out of the whole bunch of features we have for model building have high magnitude of values with them. And our machine learning model likes to see all the contributing individual features at a same scale. It doesn't want to give undue advantage to one or two features just because of the high magnitude of values. And that is why before putting or feeding these features or data into model building, we make sure that all these features are at the same scale. First of all, let's try to understand the difference between the two. Transformation adjusts the values of your numeric data to a common scale without changing the range, whereas scaling shrinks or stretches the data to fit within a specific range. Now let's understand this with the example data you see on your screen. I have here two independent variables, monthly income and the age of the customers. And I have a dependent variable, namely the purchase of a car model by the customer. Now, if I try to scale, if I try to do a simple scaling on my numerical data in order to bring them to a same scale or same range, I would probably go at monthly income and just divide this monthly income by a factor of probably 100. So if I do that, the values I get are something like this. Now, if you see, initially, the range in monthly income was right from 700 to 6,000, which has now become from 7 to 60, as compared to the range of age of customers, where it is starting from 26 and goes up till 47. Now, if you see the entire transformation, what we have done to one variable, we've tried to bring that variable down to the scale of another feature, which is age. While we have more or less done that, and it's more of comparable features now, but you see, there is still a difference between the range, which starts from 7 and goes up till 45. While a simple technique of scaling does help in bringing down the scale quite a bit, but what if I had a technique which could bring the range of the two features to exactly the same number? For instance, if there would have been a technique where monthly income was between 0 and 1, and similarly, even the age of customers was between 0 and 1. If I had such a technique, wouldn't it have been a fantastic thing to have? Because now not only do I have the two features which are on the same scale, I also have the extreme ends which are exactly same. Now, does that mean that I am tweaking the data or manipulating the data completely? Not actually. What I'm trying to do is bring them to the same scale and same ranges, but I want the data distribution to still be the same. I don't want to change the distribution of the data. So while scaling, a simple scaling just means dividing or multiplying by a scaling factor, transformation would be more rigorous or a more sophisticated technique, which kind of helps me a little bit more in bringing not only the scale in the same range, but also the extreme ends in the same range. So now let's talk about the transformation in general, or the transformation techniques which we have for our use. Now, the most popular transformation techniques which we'll discuss more in depth today are normalization and standardization. Apart from that, we also have techniques like quantile transformation, log transformation. Typically helps me when I have a handful of values which have many points, while most of the values have fewer points. So, for example, cases like the movie ratings. Okay, so a lot many people tend to rate fewer of the movies, while the rest of the movies get very little rating. Winsorization, again, a very simplistic technique where I just clip the data from extreme ends. So if I have the data which is beyond the scope of my whiskers, in this case, I have drawn a simple box plot. So what I'll do is I'll simply clip off the numbers above this whisker, or above any point for that matter. And I'll say that all the values which are outliers or beyond a certain point would be replaced by this point. And then I also have techniques like power transformation and unit vector scaling. Now let's focus on the two techniques called normalization and standardization. So normalization is a technique where I bring down, as discussed earlier, I bring down the scale and range of the entire data feature into a very restricted or a constrained range, 0 to 1, or even -1 to 1 in few cases. Now, let's discuss about the case of 0 to 1 in today's session. So we do that using this simple algebraic formula where I transformed my simple data x by subtracting the minimum value of the entire feature, x minimum, and dividing it by the difference between the maximum value and the minimum value of that. So for instance, let me just go back a couple of slides. So if I have to convert monthly income into a transformed variable, which is monthly income transformed, what I'll simply do is I will start applying the formula we just saw on the other slide on every row of this data. For instance, 1800 will just do 1800 minus the minimum value of this entire feature, which is 700, and divided by the maximum value, which is 6000, minus the minimum value, which is 700. And this would give me some value within the range of 0 to 1. So using this formula, I convert my data feature into a transformed data feature. So if I have to look at in terms of a figure, how does that happen? I have converted both income and age, and I have represented it as a scatter plot for the original data and then for the transformed data. So if you look at the data distribution, first of all, the data distribution in both the cases look very much similar. Whereas The thing which changes is the range of the data. So monthly income, where in the original data it was from 0 to almost 6,000, in the transform data, it lies within 0 and 1. Similarly, the age, which was somewhere from 26 till 49, now my range is between 0 and 1 for age as well. So with this transformation, what I do is I fit the entire data between the range of 0 to 1. And we can very well implement this using Python. And the function which we use to implement this is min-max scalar under sklearn library. Now, similar to this, we have another technique, which is standardization. Now, what standardization does is, it is again, it's on the same lines of normalization. Only thing which is different in this case is it's using a different algebraic formula to transform the variable. And the formula we have in front of us is this one, instead of x minus x min over x max minus x min. So what we have is x minus mu over sigma. Now, what is mu and sigma? We have discussed this in one of our other videos. I'll put a link to that video in the description box. But for now, just understand what mu is. Mu is nothing but the mean of the entire variable, and sigma is the standard deviation of the entire variable. So now when I implement this formula on the entire variable, what I get is something what we know as Z scores. Now, if I plot the Z scores for the original data I had of monthly income and age, I get a graph of something which looks similar to this. So contrary to the graph what we saw in normalization, we saw the data ranging between 0 to 1. In this case, I get a data which ranges from minus values to plus values across both the variables income and age, because we are now plotting Z scores for all the X values. Now, the thing which is worth noticing here is, again, my data distribution looks exactly the same as it is with original data. Now, this can be implemented using a Python function, which is standard scalar, again, coming from a library sklearn. Now, normalization doesn't actually need any particular distribution to be implemented. And thereby, it can be used in non-parametric algorithms like KNN, K nearest neighbor. Standardization, on the other hand, more implemented on normal looking distributions or Gaussian distribution. Unlike normal distribution, where everything is compacted between 0 and 1, standardization doesn't do anything of that sort. Even if you have some extreme looking values, they are not fitted within a certain range, a predefined range. It retains that information about the outliers. But at the same time, it also makes algorithm less sensitive to those outliers. So whenever I want to make sure that my model has some information about the outliers, I mostly use standardization. All right, so that's more on this topic of data transformation using normalization and standardization. Now, other similar topics which go into data pre-processing are one-hot encoding, which is nothing but converting my categorical data into some numerical codes. Then something what we more often than not do about the data before feeding it is missing value treatments. We tend to remove outliers, and Winsorization is one of the techniques to do that. In fact, other things also. We have spoken about standardization, how it retains the outlier information, and normalization, which completely does away with outliers. So all these techniques are also used for outlier treatment. Then we have a lot of feature engineering techniques which we do on the data before putting it to modeling. And dimensionality reduction is one of those techniques where we kind of bring down the dimensions or the number of features we have in the data. So that is all I have for this session. Hope you enjoyed this session. Thank you for watching this.